Hello and welcome to our presentation on global illumination based on Surfels, or GIBS as we like to call it. I'm Henrik Halen from Electronic Arts Seed R&D Group. This presentation and much of the technology behind it has been put together by myself and Kyle Hayward from Electronic Arts Frostbite, and Andreas Brinck and Shanshin Bei from EA's Ripple Effect Studios. Today I will be presenting together with Kyle. Global illumination based on Surfels is a solution for calculating indirect diffuse illumination in real time. The solution combines hardware ray tracing with a discretization of the scene geometry to cache and amortize lighting calculations across time and space. It requires no pre-computation, no special meshes, and no special UV sets. GIBS supports high-fidelity lighting while accommodating content of arbitrary scale. The original GIBS algorithm was implemented in 2018 as part of EA Seed's Pika Pika ray tracing showcase. It was developed for that demo primarily by Tomasz Stachowiak. Since then, the algorithm has been significantly extended and optimized to handle any geometry, including skin characters and large environments, while improving convergence times and quality. The algorithm is now part of the suite of tools available to developers and teams throughout EA as part of the Frostbite engine. Today, we'll talk about how we discretize the scene into Surfels. We'll describe our nonlinear acceleration structure. We describe how we integrate irradiance, how we mitigate artifacts, sample scenes with large numbers of lights, and handle transparency. Finally, we'll look at performance numbers. Before we begin, we should mention that this technique is still very much in development, and as such we expect to see significant improvements as development continues. So, let's get into the algorithm. In GIBS, Surfels discretize the scene on the fly, as geometry that needs indirect lighting comes into view. Once surfelized, the scene efficiently accumulates and caches irradiance. We believe this is a good fit for global illumination. In contrast to, say, ProGrid solutions, we perform and cache ray tracing operations exactly where they're needed, on the surfaces in the scene. In contrast to screen space filtering and caching techniques, the Surfel cache is persistent as Surfels go in and out of view, saving us from doing all that work over again. Surfels are resolution independent, allowing for a scalable solution in terms of performance and quality. It's also fully dynamic, allowing for complex dynamic lighting interactions in scenes where everything can change. GIBS accelerates production by removing the need for time-consuming bakes and the setup of traditional lighting techniques such as the creation of special meshes or UV sets. We support environments of arbitrary scale and fully dynamic environments and worlds. So, what are Surfels? Well, in the same way an image can be discretized by dividing it into pixels, we can also discretize a geometric surface. One way of doing that is by using Surfels, a shorthand for surface elements. A surfel is defined by a position, a radius, and a normal, and approximates a small neighborhood on a surface near the given position. So how do we discretize the scene into Surfels? Well, in our case, we spawn them from the G buffer as geometry comes into view. After that, Surfels are persistent, which allows us to efficiently accumulate radiance over time and to cache those costly operations without throwing the work away. Here, we've slowed down the Surfelization of the G buffer so you can see it happen in real time. As geometry comes into view, the spawning algorithm fills any gaps in coverage that appears. Normally, this is fast enough to appear immediate to the user. You never really see any gaps in the coverage. The actual spawning algorithm works by filling gaps as they're seen in screen space. The screen is split into 16 by 16 tiles. Each tile finds the texel which has the least coverage currently. If this coverage passes a randomized threshold, we spawn a new Surfel using the geometric information from the G buffer. Once a certain amount of coverage is achieved, no more Surfels are spawned in that tile. For more details on the spawning itself, I recommend Tomasz's talk from 2018. While Surfels are persistent once they spawn, they do update their position every frame in order to follow the surface they spawned on. To accomplish this, Surfels track a unique transform identifier of whatever geometry they're attached to. This identifier is written to the G buffer and picked up by the Surfels during spawn. This image is a visualization of these IDs. In Frostbite, a global transform buffer is maintained, for Surfels and other purposes. That contains the transforms of any geometry in the scene, including skin bones. Each frame we use the Surfel's relative position together with the transform ID and the global transform buffer to compute a new world space position. The obvious use case for this is for rigid geometry, but it also works for skinned meshes. When skinned geometry write their transform IDs to the G buffer, they write the ID of the bone with the highest skinning weight. This allows for essentially one bone skinning of Surfels to geometry skinned with any number of weights. Because we only use one bone, there are situations where Surfels don't follow exactly, but the Surfel application algorithm is fairly forgiving in those circumstances. Since everything is assumed to be dynamic with GIBS, skinned and moving geometry both interact with the rest of the solution just like static geometry does. Skinned geometry casts and receives global illumination. The surfelization of the scene works at any distance. Surfels are scaled so that their projection in screen space is roughly constant. This is true both when they spawn, as well as when we move through the environment. In this view, as we approach the top of the hill, you can see that the Surfels shrink. As they do, we spawn more Surfels to maintain the same ratio of Surfels per screen space area. The reverse is true when we back away. Surfels grow and we can remove Surfels where coverage is too high. The obvious impact of this is a constant level of quality at all distances, but the implication is the same for performance as well. Since we're dynamically spawning Surfels as we move through the level, the question may be asked, how do we keep memory and to some degree performance consistent? The Surfel algorithm allocates all the resources required for Surfel management upfront. This means that there are limits to the number of Surfels that are available. To effectively make use of the available resources, we employ a Surfel recycling algorithm that removes Surfels that are deemed no longer to be relevant. The way this works is that a stack of available Surfels is maintained at all points. The stack is initialized on level load to contain indirections to the entire Surfel space. As we move through the level and Surfel spawn, the stack counter is decremented on the GPU by an atomic operation, and the IDs of the Surfels on the stack are retrieved as they spawn. When a Surfel is recycled, the stack counter is incremented, and the Surfel writes its ID to the pre-allocated stack buffer. As with anything else with this algorithm, this is all done on the GPU. In the video on the left here, on the bottom, there's a bar that shows the total number of live Surfels out of the total global budget. While the recycling algorithm keeps the number of live Surfels in check, we don't want to recycle Surfels unnecessarily. That would throw away all that hard work done to calculate the lighting for that Surfel. For this reason, we employ a recycling heuristic based on some factors. These factors include how many Surfels are currently live, when the Surfel last contributed to the lighting of the scene, and how far away the Surfel is. These factors are combined and compared to a random number pulled from the uniform distribution, giving Surfels that are less relevant a higher probability to be recycled. Now, many parts of the algorithm require quickly finding Surfels that are in the vicinity of a given position. The original Pika version, a uniform grid was used to accelerate these queries. Here's a visualization of that from up top. We have a view frustum here in yellow and some green geometry in the scene with Surfels attached to it. We insert all the Surfels into this structure every frame. First, a Surfel finds its current position in the grid, which is a simple operation because it's a uniform grid. But Surfels have a radius, so we check to see if the radius overlaps any of the neighboring cells as well, and insert it there as well. We guarantee that the radius of a Surfel is never larger than the side of a grid cell, so we only have to worry about the immediate neighboring cells. This uniform grid worked well for the small level of Pika, but represented a problem when we tried to move to levels of the size of modern games. As we mentioned earlier, the radius of the Surfels are adjusted to be roughly constant in screen space, which means distant Surfels will have a large radius. To avoid discontinuities when we apply lighting or look up Surfel information, we would have to use a very large grid cell size, which would kind of negate the cost of and the benefits of using a regular grid. What we wanted is an acceleration structure with the properties similar to the projection transform, where we had more resolution close to the camera. We also wanted something reasonably simple to make sure lookups remain fast. After some experimentation, we settled on a structure where we keep a uniform grid for an area close to the camera, combined with a trapezoidal grid along each principal axis. The thickness of the slices of the trapezoidal grid increase with distance from the center of the structure. And this is a 3D image of what that will look like. So this gives us an acceleration structure that perfectly fits the way surfels grow with distance. And since the trapezoids are essentially regular grids, they just have a nonlinear transform, lookups and insertions are still very fast. This is a debug view mode of the cells where you can see the gray central grid in the middle, which grows linearly, as well as the surrounding non-uniform grids in pink, green, and yellow here. And as you can see, the trapezoidal grids in the different colors here maintained a constant grid cell size regardless of distance. It even sort of looks like an optical illusion where the sky has the same cell size as the rocks that are much closer to the camera. This is a heat map that shows the number of surfels per grid cell, and in areas where there's more geometric complexity, we get a lot more surfel spawning to cover the geometry there. So those areas tend to show a bigger concentration. So how is surfel lighting actually applied to the screen? Well, first we reconstruct the world space position of each screen space pixel. Then we find the grid cell in the acceleration structure that overlaps that position. And then we can fetch all the surfels that have been inserted in that grid cell. We then loop over all those surfels and essentially treat them as virtual point lights, applying irradiance to the current texel, weighted by their orientation and distance of the source pixel's position and orientation, among other things. Now, in certain situations, as you apply lighting in this way, you might start to see some kind of blotchy artifacts, like on the wall here and in the ceiling. And the same is true in this scene as well, on the floor next to the wall. And what's happening here is that there's surfels that have previously spawned outside in a brighter environment, and they're just applying lighting within their radius to anything that's close to them. And the reason for that is surfels don't really know inherently what's around them. And in order to mitigate that and to inform the surfels, so to speak, of what's in their environment, we construct a depth function around each surfel. The depth function is initialized to the radius of the surfel. And if there's any geometry within that radius, as we shoot rays when we accumulate irradiance, we update the depth function to represent that geometry. But we don't just store depth, we store a moving average of depth and depth squared. This allows us to recreate not just the estimate of the mean, but an estimate of the variance as well. We can use the mean and the variance to use Chebyshev's inequality to do depth testing. This provides a smooth depth test that works great for recreating slopes in depth space. This technique is obviously inspired by variance shadow maps and DDGI. In contrast to DDGI, we only care about the depth within the surfel diameter, so we have a bit of a head start there. And we only care about the hemisphere. This, in combination with Chebyshev's inequality, works amazingly well, even with really low resolution depth functions. In our case, it's configurable, but most of the time we just use a 4x4 texel depth map per surfel hemisphere. And that's enough to get rid of the artifacts. In the image to the right here, you can see we no longer have those weird blotchy artifacts on the wall. And it's fixed in this environment as well. So how do we actually calculate lighting for surfels? Well, since everything is dynamic with GIBS, we can support emissive surfaces and materials. We want to support destructible and dynamic environments. And we need to be able to efficiently integrate the irradiance in these situations and react to changes in the scene. The basic algorithm is pretty simple. Here we have a synthetic scene where we have some surfels on the ground. We have a sky above the scene in blue and a light and some other geometry in there. To accumulate the irradiance, we just shoot rays randomly into the scene. And if we miss everything, we assume we hit the sky and we evaluate sky lighting in that direction. If we do hit some geometry, we need to evaluate direct lighting from the lights in the scene. So we need to shoot occlusion or shadow rays towards those lights. If those rays hit something, there's no contribution for that direction. But if we don't hit anything, there's a contribution for the light. We can evaluate the BRDF at the hit location and send the results back to the original direction. But we can do a little bit better than that. With this technique as described so far, we get single bounce lighting essentially. But there may be surfel coverage on those hit locations as well, and those surfels over time have accumulated irradiance as well. So accounting for those contributions, we can essentially get infinite bounce lighting over time. Now, as I mentioned, we want to support in dynamic environments and reduce the cost of ray tracing as well over many frames, so we don't have to shoot all the rays to accumulate lighting at once. And to do this, we use a modified version of a moving average estimator. With a regular moving average estimator, you'd have to choose a blend factor for each sample. This means you sort of have a choice between either something that's really reactive to changes in the scene or something that converges well over time. What we really want is the best of both worlds. We want it to be automatic. So in addition to accumulate a longer term moving average, we also track a shorter time mean and a short-term variance estimator. These short-term estimators are used to adjust the blend factor for the long-term mean. This allows us to quickly react to changes in the scene while also converging to a noise-free result. And I'm going to again refer to Thomas's presentation from 2018. And I should mention there's code on GitHub for the multiscale mean estimator as well. Now, since we're tracking variance per surfel, we can make good use of this for other purposes as well. The number of rays sent for each surfel every frame depends on a few different factors, one of which is the variance that the surfel sees. If a surfel sees high variance, it requests more rays in order to converge faster. And in contrast, if we see low variance, it can send much fewer rays. And we use this to quickly react to changes in the scene while reducing the overall ray count when things converge. And in fact, we can go down to an almost dormant state for surfels, where they send just enough rays to be able to detect that something changes in the scene. Here's a visualization of this at work. In the view on the right here, blue represents low variance and red represents high variance. And as there's a change in the scene, you can see that the surfels see a lot of variance. This means they start sending more rays to react and converge quicker. The same is true if we change the lighting in the scene here. Surfels start to see a lot of variance, they quickly up the ray count, they converge, and then can go back to this almost dormant solution where they send maybe a ray once per frame, or even less than that, a ray every few frames. The same is true when we visit a new area and we just spawn new surfels. When we surfelize the scene, surfels tend to show a lot of variance because they haven't converged yet. But once they do, we can go down to that almost dormant state pretty quickly. We also enforce a global ray budget that's based on the total number of rays that all of the surfels request individually, compared to a global user-defined budget. That way we can enforce a global budget and a predictable performance target. Now, as we're shooting rays into the scene, the naive way to do it would be to just send rays uniformly across the hemisphere. We can do a bit better than that because we know that our BRDF is Lambertian, so we can import and sample the cosine lobe, which means we send more rays in the direction of the where the BRDF is larger. And this works pretty well in most environments, but there are some situations where it doesn't work well at all, especially situations where the cosine lobe is not the direction where the light is coming from. So here's an example of a scene like that. We have two surfels here. Most of the light in the scene is coming from the wall on the right side that's hit directly by sunlight. The rest of the scene is really dark. Now these two surfels actually send the same number of rays in the same directions, but the surfel on the right ends up hitting this light source twice as often. And what that looks like in reality, when surfels have a bad estimate of what the actual irradiance should be, is noise that you'll see on the left side in this image. Now what we really want to know in this scene in particular is exactly how much light is coming from this direction on the right here. The rest of the scene doesn't really matter because there's very little light coming from those directions. Now one way to figure that out would be to just send a lot more rays, but we don't want to do that because that's expensive. So what if we could send more rays in the directions that matter, where more of the light is coming from? Well, that's ray guiding. Our solution for this was inspired by practical path guiding for efficient light transport simulation by Müller et al. And probability trees by McCool et al. Müller's solution creates a quad tree of the sphere on each node in a spatial binary tree, where each leaf node in the directional quad tree that represents the sphere in a spatial location has equal radiance associated with it. So it's subdivided until each node has equal radiance. This is then used to importance sample using the techniques from McCool et al. And this generates rays in directions proportional to how much radiance is coming from those directions. But we don't really want to construct a quad tree every frame for every Surfel. So what we do is we map the hemisphere to a quad where we track irradiance in directions instead. The visualization on the left here is just a small subset of a number of Surfels updating their irradiance maps. The size of the map is configurable, but for most applications we use 6x6 texels. We use 8 bits per component plus a single 16-bit scaling value per Surfel. We normalize the entire function after each iteration. And now that we have a discrete function, we can importance sample that. And I'll just quickly describe how you would importance sample in a general discrete function. What you would do if you have a function like this is you pull a random variable from the uniform distribution, you multiply it by the sum of the discrete function, then you start walking the function, and it doesn't matter from where you start walking as long as you're consistent, and you start accumulating irradiance, or the value of the function. And once you reach a sum that's equal to the uniform distribution that you just pulled, then you have your importance sample variable. So what this means is a variable will be produced in proportion to where the function is larger. And we can do this for our 2D function as well, even though it's not a 1D function like I just showed. We can treat it as such. We can pull a random variable, we can multiply it by the sum of radiance across this function. And we can start walking the function and accumulating. And when we hit a sum that's equal to or larger than the random variable we pulled, we have our direction, we have our importance sample direction. In our case, this is in UV space, so we do the inverse of the hemisphere to quad transform. And now we have a importance sample ray direction based on the radiance in our radiance map. Now we can do this in a hierarchical way as well, as McCool et al. Points out. And in our case, we can use a linear filter tap in the intersection of texels in 2 steps for a 6x6 function. So we can do a 3x3 walk of importance sampling, and then do a 2x2 for the texels that cover each texel in the higher level map. And if we account for the PDF in at each step, and fortunately enough, the PDF is equal to the value of the function at that location, we can do this in an unbiased way. Now, to verify that this is all working, we created a small test bed where we can bring in an HDR map. And if you look at the HDR map here on the right side, if you imagine that the Surfel is on the floor with the normal pointing up, that's how we sample these environments. On the left side, you'll see the experiment itself, where on the x-axis we have the number of samples, on the y-axis we have the relative error, and the blue curve is the cosine lobe importance sampled sampling pattern, and the yellow curve is the ray-guided version. And as you can see, after a number of initial samples, the ray-guided version kind of learns where to send rays and quickly converges much faster. Same is true for this scene. It's kind of a similar situation where most of the light is not coming from the direction of the normal, where the cosine lobe would normally do a good job. Most of the light is coming from other directions, which is exactly where ray guiding would benefit. Now, there's obviously scenes where ray guiding doesn't really help, and the cosine lobe just does a perfectly fine job. And this is a good example of that, a scene where the lighting is just really uniform and matches the cosine lobe pretty well. And there are scenes where none of the solutions really work well. In this situation, we have some really small, bright sources of light, and our ray guide is just too low resolution to really pick those up efficiently and send rays in the right direction. Fortunately, in a scene like this, in a virtual environment, we would actually directly sample those light sources. They would be analytical light sources. Now, in addition to the optimizations I've just talked about, we also allow Surfels to share irradiance between themselves. This is enabled by the acceleration structure. Surfels inherently know which cell they're part of in the acceleration structure and are able to access other Surfels in the same grid cell. This allows us to essentially apply a weighted irradiance sharing across Surfel boundaries, which can really help convergence in certain scenes. Here's an example of that. This is the result after just 64 samples with no radiance sharing. And it looks pretty blotchy, as you can see. And this is the result with irradiance sharing. So after just 64 samples, we have a pretty reasonable result in this scene. Another scene, it's maybe not as difficult. It's outdoors. Should converge pretty fast, but after just 64 samples, we have a pretty blotchy result again. And with irradiance sharing, the results look a lot better. So that's it for me, and I'm going to hand over to Kyle for the rest of the presentation.
Thanks, Henrik. I'll now go over our many light sampling research, transparency support, and some performance numbers. But first, let's quickly cover how we sort our rays. Shooting rays with little spatial coherence causes poor performance on most platforms. Executing threads tend to go down very different parts of the acceleration structure, which results in poor cache utilization. So to alleviate this, we've opted to use a sorting strategy similarly to Battlefield 5, known as ray binning. We bin rays based on their position and orientation. We simply use the Surfel cell coordinate converted to 1D for the spatial hash. This is the dominant value when calculating the bin index. And then we use the ray shot from the Surfel as the other part of the bin index. Then we run 2 passes that generate the reordering information we need to sort the rays, followed by a final pass that reorders the rays based on the previously calculated bin counts and offsets. You can see the Battlefield 5 presentation for more information on this. So far we've discussed how we integrate lighting, but how do we light the intersections? Let's talk about our research into many light sampling techniques. Many light sampling is an ongoing area of research within offline and online computer graphics, but there have been recent advancements in the last 2 years that have been really promising, and we'll discuss our application of those techniques. This scene, which is a map from PVZ, is one of our stress tests and contains 1400 lights inside the camera frustum. And here's the indirect diffuse for this scene. So, what are our options when it comes to sampling hundreds or even thousands of lights? Once you move beyond a few lights, it is no longer feasible to sample all the lights in the scene. A first step solution is to stochastically sample n lights, where n is less than the total number of lights. This might work well when there are tens of lights in an area and is also dirt cheap performance-wise if n is small. However, once you move to hundreds or thousands of lights, this approach starts taking way too long to converge. So, we need some sort of importance sampling to combat the convergence problem. We've investigated a few solutions, and I'll present the 2 most promising avenues: stochastic Lightcuts and reservoir sampling. The first solution I'll discuss is stochastic Lightcuts. This solution is based on the work of Chen from HPG 2019. Stochastic Lightcuts build upon Lightcuts by minimizing bias sampling of the light tree and improving sampling efficiency. This research is attractive because it does not need a large amount of samples to converge and requires no spatial or temporary storage beyond the light data structure, unlike resampled reservoir sampling, which we'll cover in a few slides. So how do we build our light tree? We store light positions in view space for precision and sort the lights based on a Morton coding of their position. This sorting helps group lights spatially so that the tree has implicit spatial correlation, and we don't need to do multiple sorts during construction as you would with BVH tree construction. We then build the tree bottom up, where each internal node represents the combined bounds and intensities of the children below it. Now that we know how we build the tree, let's walk through the process of sampling. To sample the tree, we first choose a cut through the tree based on a user-defined node limit. This is typically 2 to 8 nodes, depending on quality level or platform. This count corresponds to the number of lights that we will eventually shoot rays towards to compute visibility. We compute the cut through the tree by choosing nodes that minimize the lighting error based on the sampling position compared to the nodes in the tree. Once we've computed the cut, we traverse stochastically down the tree from each root node in the cut. For each internal node, we assign probabilities based on importance weights to its children, and then randomly select the left or right child based on its probability. Another light sampling solution we've investigated is reservoir sampling, based on the restore research by NVIDIA. Unlike Lightcuts, reservoir sampling requires no pre-computed data structure for the lights. Also, another benefit is that it only requires 1 ray per chosen sample, which makes it cheaper on consoles compared to our implementation of stochastic Lightcuts. The essential idea behind reservoir sampling is that you stochastically evaluate N lights, but only choose M winners to shoot rays against. In our case, we randomly sample 4 to 8 lights and choose only 1 winner. The winner is chosen by calculating the weight of the light based on its distance and intensity. We then generate a random number, and if that number is less than the weight of the light divided by the total weight, we select that light. And finally, we normalize the resulting PDF by the total weight of all the sampled lights. The downside here is that in order to get the most out of reservoir sampling, you really want to compare spatial and temporal samples to your currently chosen reservoir sample. And this is called reservoir resampling. This is a bit complicated to do for indirect lighting because a naive approach requires a lot of extra storage to save your chosen sample, to then later compare against other temporal and spatial samples. And this is an area we're currently working on supporting. Now I'll show some examples of each technique. In this shot, we have around 700 lights in view, with another 700 outside the frustum. And here's the indirect diffuse of that scene, after it has converged to acceptable quality in about 5 seconds. In the following slides, I'll show each technique after solving for only 15 frames. The first example here is 2-sample brute force random sampling, which means we will shoot 2 shadow rays. We can see that this is very noisy, and we're missing a ton of light contribution. Now we have 8-sample reservoir sampling. It's getting much closer to our Converged example, far outpacing random sampling, but it's still quite noisy, as we can see with all the splotchy fireflies. And finally, we have 4-sample Lightcut sampling after 15 frames. This is much closer to our Converged example, but also much more costly on console. And again, here is the Converged Indirect Diffuse, and I'll cycle between Lightcuts after solving for only 15 frames and the Converged example. We can see that it gets very close to the Converged result even after only 15 frames. So far we've described our solution for opaque surfaces. Now let's talk about how we are going to support transparency. But first, here's a gratuitous lighting shot showing off our lighting for transparency. While the Surfels are perfectly fit for caching irradiance for opaque surfaces, it's hard to port the same method to transparency because we rely on spawning Surfels from the G buffer. To address this issue, we apply the Surfel algorithm for light probes. The ray trace probes will persist in a probe volume and gather radiance similarly to Surfels. Because we are gathering the diffuse radiance, it gives us the opportunity to project probes to spherical harmonic space. In addition, we use the same adaptive integrator that we have discussed earlier with Surfel integration to accumulate probe samples across frames. As we can see, it's hard to compute the integral for the SH coefficients in a single frame in real time because it needs a large amount of samples to converge. We amortize the calculation across frames. The irradiance SH coefficients on every frame are calculated by sampling incident radiance with only a few rays and projecting to SH space. Then we use the same adaptive MSME integrator as Surfels to accumulate the projected radiance across time. The integrator will also calculate the number of rays to shoot in the next frame, depending on variance. The issue of scale is a problem for light probes, just as it is for Surfels. We investigated a few different schemes, but settled on volume clip maps. These are a set of nested volumes, which each level represents larger and larger area, but less detail. The structure enables relatively high detail close to the camera, while still covering a large amount of area for a low memory cost. We can also update the structure out of sync, and use lower detail levels to prime higher detail levels. Now, let's take a closer look at how we update the clip map when the camera moves. First, we check the world space position of the camera every frame. If the camera moves outside of the center grid of any level, we shift the probes of these levels towards the camera to keep it in the level center. The distance of shifting depends on how many grid cells the camera has moved away from the center. After the shifting, there will be new probes which are spawned in the updated clip map, and these will be initialized with higher level probes using interpolation. Because the hierarchical grid covers a large area in world space, most probes will still be valid after updating, which means they only need to be copied to their new coordinate in the probe volume, instead of wastefully being discarded. This is the key to keep the stored irradiance valid for as long as possible and improve performance. Here's a demonstration of the probe volume updating its coordinates as it follows the camera. Now I'll show how the clip maps are set up spatially. Here we have all 4 levels, and now just the first level, the second level, the third, and finally the 4th level. And here we have a map from PVZ where we show the debug view, showing which pixels are sampling from which level. We've frozen the clip map camera and we can see the clip map hierarchy expanding outward from the bottom center of the screen, with the highest detail in the bottom center and the lowest detail in the horizon. Sampling the clip map is straightforward. Find the highest detailed level that contains the shaded pixel, then sample the SH coefficients from the 3D clip map texture and reconstruct irradiance. However, this naive sampling strategy will cause visible discontinuities on borders, as we can see here with the statue. This is perhaps even more of a problem for animated scenes. You can see the statue pop to the lower detail level in the video. A simple solution is to blend samples from the 2 closest levels. We create a transition border for each level. Pixels lying in this border will sample from the current level and the next lower or higher detail level. We calculate the blend weight based on the normalized distance to the border. Now with blending enabled, as we back the camera out, we have a smooth transition. But blending has the extra cost of sampling 2 volumes per shaded sample. Our goal is to sample only 1 volume while maintaining a similar quality to blending. Introducing blue noise dithered sampling. Blue noise is a great low discrepancy distribution which is easily filterable and works well with our TAA. The blue noise dithering is similar to the blending solution. We sample from the current level or the next level based on the screen space sampled blue noise value, resulting in a quality similar to blending. So as we move the camera, we can see a smooth transition, albeit not with as high quality as with blending. Here's an example to show how our solution for transparent objects works well under a fully dynamic world. No pre-computations are needed, and the probes will automatically update when the scene geometry or lighting changes. But at the same time, we quickly converge to the new environment. Let's talk about where we're at with performance of GIBS today. I'll go over our general frame structure and then give some performance examples of our worst case scenarios, followed by scenarios that are more representative of game content. Here's a general overview of our frame that we've detailed until now. There are 4 general sections: persistent surfel work, spawned work, filtering the surfels, and then finally applying the surfels to the screen. Generally, the ray tracing work dominates the persistent work. For spawned surfels, depending on how many are spawning in a frame, the ray tracing or the geometric normal reconstruction can dominate. Or, depending on resolution, the gap fill can dominate. Filtering is generally very fast, averaging only around 0.2 milliseconds. And finally, for surfel application, the lighting apply pass dominates this group. All the numbers and timings that follow have the following settings. we're testing on a PS5 with 4K output resolution, which means our screen space passes run at 1080p or 1/4 the area of the output resolution. We're not limiting how far the Surfels are spawned or cutting off rays at a certain distance, and we're using 8-sample reservoir sampling unless otherwise noted. Lastly, we're testing the worst case for our solution, starting from an empty Surfel scene and then to converge to acceptable quality. Once we've converged, the costs trail off, so we'll focus on the expensive part in the next few performance examples. Here's example scene 1, using Plants vs. Zombies town center map with only sunlight. And here's the indirect diffuse after we've converged to acceptable quality in roughly 3.5 seconds. Note, some of the albedo colors used for GI are not 100% true to the albedo textures. In this scene, due to the large draw distance, we average roughly 7 milliseconds total. But as you can see, we're solving, spawning, and ray tracing Surfels all the way to the horizon. And here's scene 2. This is the same view we showed earlier when discussing our mini light solution. This is our stress test scene with 1400 lights in view. It converges in, well, yeah, it converges in basically never. But let's have a look at the performance anyways. We can see that there is a bit of a tax when it comes to sampling local lights compared to the daytime example. But this also takes ages to converge. So what does it take to converge? Here's the same scene, now with a 1 million ray budget. And we're now converging in around 10 seconds. And it's still quite noisy, but it's getting there. And looking at the performance, we can see we spike quite high when the Surfels initially spawn and start solving, but then it levels off quite fast. Albeit, it's still quite high, pushing 11 milliseconds once we've started to converge. This is one of the areas we want to excel at, so we still have some work to do here to improve. Here's scene 3. This is the same scene with 1400 lights, but now a different view. And this now converges in around 7 seconds. And as you can see, it's quite a bit cheaper with our more constrained view, and it also converges much faster. But what if we want faster convergence? Here we do the same test, but with 4 sample light cuts. And this time we're converging in around 5 seconds. It's pretty costly to gain the advantage of convergence time, as we can see now that the average is around 11.3 milliseconds. Converging fast in scenes with many lights is still actively under development, but I think we have a promising start here. Also, you can see on the right of the graph both persistent and spawn are trending downwards as the variance is stabilizing. And finally, our last scene from an internal demo. This level has around 140 lights, and we can see it converges in around 2 seconds with this constrained view. Performance here is even better than in the street view from PVZ, with averaging around 5.5 milliseconds. Now I'll show a couple of examples of roaming around the scene 1 from PVZ, something more representative of real-world performance, as Surfels will constantly spawn and need solving while moving through the level. But we won't ever be starting from 0 except from the very beginning. Here we have the same settings as previously, and we can see performance is better than in the stress test, averaging around 5.4 milliseconds. And here we have relatively the same path as a previous slide, but now using an output resolution of 1800p with checkerboard rendering enabled. This test is more representative of the settings we expect games to use, and we can see we're quite a bit faster here, averaging around 3.4 milliseconds. We still have our work to do, but it shows we're in the ballpark in performance. And finally, here's an example of the cost to solve our clip map probes. This follows the same route in the previous free roam tests. We have a 3-level clip map, and the cost is very reasonable. We cycle which clip map we solve every few frames. The 3rd clip map is the cheapest, as the most rays or misses, as can be seen in the graph. It's hard to judge performance of the sampling cost of the probes, as it depends on the number of transparent pixels. But if we were to sample every pixel full screen at 900p, this is roughly 0.2 milliseconds. So that about sums up where our GIBS technology is at today. Here are some details on where we're headed. Currently, we don't support procedural geometry explicitly. Procedural geometry works, but it will continuously spawn and recycle surfels because we do not track them across the surface as we do with skinning. We also have certain situations where a high detailed geometry can overspawn surfels. One of our options is to combine with screen space global illumination to minimize surfel spawning in areas where SSGI solves well. Combining with SSGI also helps limit how many surfels we need to solve, and it will help limit how far out we can cull surfels and ray tracing. We are investigating sharing guiding information across surfels in order to get a better picture of where to send rays. And we are investigating using restore-like approaches to help augment ray guiding. We still end up selecting too many dead branches or lights. If we can store visibility of our lights in our cell or voxel data structures, then we can vastly limit the lights we need to consider per ray hit. We bin and sort our rays, so it may be advantageous to share lights between these rays. For example, for reservoir sampling, we could do our spatial sample in this fashion. For temporal reservoir sampling, we are investigating storing reservoirs in the cell structure or on each surfel. Our light cut traversal is not well optimized yet and could make use of platform-specific intrinsics. And finally, we need to move our light sampling out of our ray tracing pass and schedule secondary shadow rays to later passes. Our probe clip map solution is still early days, and we are looking to add ray guiding and specular support in the future, and improve performance by integrating and sharing rays with Surfel Ray Dispatch. To wrap things up, we have seen that the opportunistic surfelization of the scene provides an efficient mechanism to cache information on surfaces of opaque geometry. The caching mechanism is persistent, dynamic, and decoupled from the output resolution. We use Surfels to cache irradiance on a wide range of geometry and scenes, and provide a fallback solution for geometry that does not fit their requirements. A lot of people have helped out in working on this and creating the presentation, and we would like to thank the Frostbite ray tracing and render core teams for bringing ray tracing support to the engine. We thank John Greenberg for his contributions and research on mini light sampling, Joe Warren, Johan Zischling, and Chris Wichitich for providing high-quality content for this presentation, Jim Royal for proofreading and ensuring the presentation meets our quality standards, and last but not least, Tom for the original implementation of Surfel GI back in 2018. Thank you for attending our talk, and I hope you enjoyed the presentation.